All right, today we're going to pull back the curtain on something called ARIMA. It's a really powerful statistical tool that can take a bunch of old data and turn it into forecasts about the future that are, well, surprisingly good. We're going to break down exactly how it pulls this off, step by step.
So let's start with a massive question like this. It's something economists and businesses have to grapple with all the time. But how do you even begin to answer it? You can't just look into a crystal ball to predict something like GDP growth. You need a model.
And one of the most reliable, time-tested tools they use is ARIMA. Now, I know it's a bit of a mouthful, but its job is actually pretty straightforward. Find the hidden rhythms and patterns in the data from the past and use those to make a really educated guess about what's coming next. It's made of 3 key parts, and we're about to unpack each one.
But here's the thing. Before we can even think about looking forward, we have to look back. We have to learn to speak our data's language. And that, right there, is our first big challenge. Okay, so here's the first rule of the ARIMA Club. The data has to be stationary. What on earth does that mean? Well, think of it this way. Imagine you're on a boat that's bobbing up and down, and you're trying to measure the height of the waves. It's impossible, right? You need to stabilize the boat first. Data is the same. For ARIMA to work, the data's average and its volatility can't be constantly changing. It needs a stable base.
And here's the catch. Most of the data we see in the real world, especially in economics, isn't naturally stationary. Just look at this graph of population growth. It has a super clear upward trend. This is shifting ground, and you just can't build a reliable forecast on a foundation that's constantly moving.
So, how do we fix this? How do we stabilize the boat? Well, that's where the I in ARIMA comes into play. It stands for integrated, and it's a clever trick called differencing. This is the main tool we use to get that stability we need. And check this out. It's actually a really simple idea. Instead of looking at the actual dollar amounts of weekly earnings, which are clearly going up, we look at the change from one week to the next. In this case, it's a steady $50. And just like that, poof, the trend is gone. We've created a stable, stationary series that our model can actually work with.
So our data is stable. Awesome. Now we can actually start looking for patterns. And we do that using the other 2 parts of the name, AR and MA. AR is for autoregressive, which is all about the data's memory. And MA is for moving average, which is about the lingering effects of past surprises or shocks.
Let's start with AR, the autoregressive part. This one is super intuitive. It's based on the idea that today's value is probably pretty similar to yesterday's, right? If the temperature today is 80 degrees, it's probably not going to be 10 degrees tomorrow. The data has a memory that carries over.
Now, the moving average part, MA, is a bit different. It's not looking at past values. It's looking at past forecast errors. Think of it as the model learning from its past surprises. You know, some unexpected news hits and a stock price jumps. That shock might not just disappear. Its effect can ripple through the data for a few days. The MA component is designed to capture exactly that.
Okay, so we've got our building blocks. The I for stability, the AR for memory, and the MA for shocks. But how much memory should the model have? 1 day? 5 days? And how many past shocks should it pay attention to? To figure that out, we have to put on our detective hats.
Our main clues, our smoking guns really, come from these 2 weird-looking charts, the ACF and the PACF. The best way to think of them is as the data's unique fingerprints. By just looking at the shapes of these plots, we can get an incredibly good idea of what kind of memory and shock patterns are hiding in our data.
And this table? This is basically our decoder ring for reading those fingerprints. For instance, if you look at the top row, it tells us that if our PACF plot shows a really sharp drop-off, while the ACF plot kind of fades out slowly, well, that's a huge clue pointing us toward an AR model. By matching the patterns we see in the charts to this guide, we can figure out the right settings for our model.
Now, a lot of the time, the fingerprints might point to a couple of different suspects, a few possible models that could work. So how do we pick the absolute best one? We use a scoring system called the AIC. It's a fantastic little tool that finds the perfect balance between accuracy and simplicity. We just test out our best candidates, and whichever one has the lowest AIC score wins. It's that simple.
But what if our data has a cycle that repeats over and over, like retail sales that go crazy every single December, or electricity use that spikes every summer and winter? A regular ARIMA model can struggle with that. It needs an upgrade.
And for that, we call in the specialist, SARIMA. The S stands for seasonal.
It takes everything we've just learned and bolts on a whole second layer of components that are specifically designed to handle those predictable seasonal cycles like the ones you see here in quarterly inflation data.
Whoa, okay. I know this notation looks kind of scary, but trust me, it's simpler than it seems. All it is two models working together. The first little set of parentheses handles the short-term, day-to-day patterns, and the second, bigger set, handles the long-term, season-to-season patterns. It's just a really powerful way to capture both kinds of behavior at the same time.
All right, we've done the hard work. We've wrestled the data into a stable form, we've played detective to find the hidden patterns, and we've picked our champion model. It's time to put it all together and see what all that work actually gets us. So, if you look back, this whole thing has been a really clear logical journey, right? We start by just looking at the data. Then we stabilize it. We find its fingerprints, pick the best model, double-check our work, and only then do we finally make the forecast. Every single step is absolutely crucial. And after all of that, after running our Australian economic data through this entire process, the model spits out an answer. It gives us a forecast for that very first question we asked, a predicted quarterly GDP growth of 0.6%.
But here's something that is absolutely crucial to understand. A responsible professional forecast is never, ever just a single number. The model also gives us what we call confidence intervals, basically a high and a low range. These are the guardrails. They're an honest admission that the future is uncertain, and they give us a realistic sense of what's possible, both on the upside and the downside.
You see, getting this right isn't magic. It's not about finding some secret mathematical formula. It's really a blend of skills. You have to know the theory, of course, but you also need to get your hands dirty applying it. And maybe most important of all, you have to be disciplined enough to constantly check and validate your own work.
And that all leads us to one final, really big question. An ARIMA model is incredibly powerful, but it's only as good as the history it learns from. So what happens when something comes along that is so massive, so unprecedented, like a global pandemic, that it completely shatters all those historical patterns? How can we possibly forecast the future when the past is suddenly no longer a reliable guide? That is the great challenge for every forecaster working today.